will be more papers about whatever the latest measurements are. Okay, so I'm going to end by showing you one more movie. All right, and so this is this movie which shows the two black holes orbiting each other against an imaginary background, but they're real stars from a star catalog. And the calculation is what you would see with your eyes or with a telescope. So light rays have been traced from every star to the viewer. And the light rays that travel close to the black holes feel the gravity of the black holes, and the light rays actually bent. So that means that when you look back along the light ray that reaches your eye, that even if the actual star was over there, you see it displaced because the light ray got bent and comes to you from a different angle. And all the sort of dancing around of the stars, all that sort of jittery motion that you saw, that's because the black holes are not at rest, but they were actually orbiting. And so you'll see sort of some of the stars appear to move around. It's just their light rays being deflected. Sure. And some of you may be able to see on the black holes their little eyebrows, their little shadow. So what you're seeing, you're seeing the black holes as shadows, right? Because those are light rays where if you trace back from your eye, those light rays, instead of ending up on a star that you can see, they actually end up in a black hole. So nothing comes out, you see black. Those little eyebrows were from light rays that when you trace them back, the gravity of the black hole is so strong that it deflects the light ray all the way around the black hole, and then only does it get captured. And so you see sort of that small little region where that is true. And if we could zoom in again, you'd see actually the eyebrows have eyebrows where you go around twice before you get together. So, what I want to emphasize is this is not this is a real, everything here is a real calculation. So first of all, the simulation that produced the two black holes orbiting each other, and then tracing the light rays, including putting in the redshift effects, because as the light rays come to you, they pass close to the black hole, right? And remember, we already discussed how the ticking rate of time changes as you go into the strong gravity, and that's related to the frequency of the light. So you see this redshift, and because the black holes move, when the light ray climbs out of the black hole's pull and comes to your eye, the effect is not symmetrical. It doesn't cancel. So you get a distortion in the colors of the stars as well. And then all the lensing effects and these peculiar way that the images move around. Everything is a calculation. And it's remarkable, again, to me, how it's taken 100 years, but basically we're at the stage of being able to do these calculations and the double bonus of having the experiment to confront the theory with. And who knows, maybe 100 years from now, our observational prowess will have reached the stage where there will actually be observations that look like this. Thank you.
So we have two microphones. I think I see one here and one over there. And Saul's been gracious enough to take questions. So we'll let people stretch their legs and ask questions. I can just say that for those of you who haven't realized, this is really, for most of us, a sort of a once-in-a-lifetime discovery, and it really brings me great pleasure to bring this to everybody here. Looks like we have a question. Please.
I was curious, you showed when the detectors found those waves, you did a simulation that matched. How did you know what to simulate? There's so many different masses and spins.
Yeah, what the experimenters actually do is they build up a template bank. So they have hundreds of thousands of waveforms which have been produced by theoretical modeling, which they use the numerical simulation. We can't do hundreds of thousands. These are just too big. I mean, a typical calculation takes a month of supercomputer time on one of the big national machines. So we can only do a much smaller number, but they calibrate the templates against the numerical calculation. So we had a pretty good idea from which templates, they tried all the templates and found, told us which ones fit very well. So we had a pretty good idea of what masses and spins to use. And then we did a couple hundred calculations, bunched around those values, and that was just one of them.
Can I do one follow-up? The time scales that you were talking about, is that a time scale just right at the very...
It's right at the very end, yeah. So when these black holes are further apart, they could take hundreds of millions of years to spiral in. It's just the last part. So the LIGO detector is only sensitive when the frequency of the waves is greater than about 10 or 20 hertz, 10 or 20 cycles per second. And so you have to wait until that last little bit.
Yeah. Thank you.
I have a couple of questions.
Yes.
The first one, are these gravitational waves affected by anything along its path, like something like black hole, for example? And my second question is, if there are multiple of these orbiting black holes or any black hole which has angular momentum, so what we get here on Earth will be the superposition of all these things. So how do we actually separate and identify where exactly these black holes are?
Right. So very good question. So the first question is the wave affected as it travels through the universe? So most of the universe is actually pretty transparent to gravitational waves, right? So, occasionally there's a star in the wave that you saw, even for the Earth. I mean, the interaction of the gravity with matter is so weak. I mean, we're used to thinking of gravity as strong, right? I mean, we can only jump a few feet in the air. But I mean, if you just take, an ordinary toy magnet, you can lift, a metal disc quite easily against the whole gravitational attraction of the Earth. Okay, so gravity is weak compared with other things, and it manifests itself in that way. Of course, if there was a black hole in the way, that would absorb the gravitational wave. But along any given line of sight, black holes are pretty small. It doesn't do anything. Then let's see. The other question was.
So there could be some multiple sources of gravitational waves.
So you might have black holes merging, at different time all over, and we're bathed in the sea of gravitational waves. So part of the LIGO experiment is actually to try to detect that. We call that a stochastic background. That's just the fancy jargon for superposing a bunch of signals where any individual signal is too weak to be picked out. But if you have many, many of them on top of each other, you can hope to see some kind of an effect. The effect from that is not this nice waveform that we saw. It's a more subtle way that those have to be detected. But they don't interfere with the ability to detect. This is a relatively strong signal that sticks up above the level of that background.
Thank you.
Yeah. Knowing what you know with the help of computers, etc., do you ever contemplate what Einstein could possibly have had going in his brain that he could have thought all this through?
Yeah. I've thought about that a lot, right? Every physicist thinks, I want to be the next Einstein, right? So I think if you look at Einstein's path, there are a few things that stand out. One is he wanted to understand and work out everything for himself. He did badly in college, partly because he wouldn't show up for exams and things like that, because he felt that he was being taught the old physics, not the new stuff. And he was being taught it in a way that was unsatisfying. And so he spent a lot of time rethinking these things. I mean, how could you come up with something like time is relative to, most of us are pretty accepting, we go to school and they tell us, time, it's, you start reading a clock and then you go, maybe you do some science experiments and you keep time and so on. We don't even think about it, but he thought about it. And I think it's that kind of questioning, of almost a questioning of authority, not being satisfied unless you understand it yourself. I think that's the hallmark of the very best scientists.
Well, the second thing is for you to take your brilliance so candidly, so effortlessly, when all of us are in awe of what you say and what you've done, etc. And I might just take issue with one little thing.
Yeah.
I think the statue of Einstein belongs in front of the White House, not in front of the Academy.
I was personally wondering, and I'm sure a couple other people are wondering this as well, in the side-by-side comparison of two color graphs of the detection, not the waveform, but the color graphs, why was the one in Washington, I think, considerably brighter than the one in Louisiana?
Yeah. So I don't know the answer. In other words, was it just the settings on their thing, the way it was done, or was it a real effect? The detectors actually have slightly different sensitivities at any given time, because it depends on, they are affected by the local background noise to some extent. So I don't know whether it was that reason or whether it was just the way, the settings on those particular pictures. I actually don't know the answer.
Okay. And how long do you think it's going to be until we have the, sort of holy grail gravitational wave detector in space?
Yeah, so gravitational wave detector in space is a big dream, because it would first of all, it would allow us, LIGO is sensitive to black holes of masses like the ones that were detected, 10 or 30 solar masses, somewhere, in that range, say 1 to maybe 100 or a few hundred solar masses. But we believe at the centers of galaxies there are these supermassive black holes, somewhere maybe 1 million or even 1 billion times the mass of the sun. And in order to the wavelengths or the frequencies of those are so low that there's no hope of measuring them on Earth. There's just too much noise in ground motion and so on. So there's been this dream of putting detectors in space. You'd have satellites maybe in equilateral triangle with the laser beams bouncing back and forth. But now you'd have arm lengths of maybe 500,000 miles or something like that, and try to do this. Anytime you do things in space, there's a big dollar factor. We're talking, several billions probably. There was a plan to do this in 2034. Because of the excitement of this discovery, it's been moved up. We're now hoping maybe like 2029. Unfortunately, the U.S. is not a major player in this because various just budget problems in Washington. There isn't really money. It's the European Space Agency that's leading the effort on this. The NASA has now proposed to restart the U.S. effort on this program, and we're hoping that that will lead to something. There's also talk, apparently the Chinese government is very interested in in doing this, and maybe that will spur Washington when nothing else will.
Thank you.
Hello. I was wondering if all black holes are going to look exactly like a 360-degree circle, and if there's any way to detect the effects of black holes before they affect us.
Right. So usually when physicists draw the black hole as a 360-degree circle, that's usually because we're representing a non-spinning black hole. So we would expect it to be spherical. If the black hole has spin, then the geometry is not spherical. It's, as you would expect, it's sort of an oblateness. So I don't know if you noticed some of the early pictures. I drew them as kind of these ovoid of shapes. We actually have precise mathematical descriptions for that geometry, what the shape actually is, at least for the quiescent black holes, when they're just sitting there. As to can we infer the presence of black holes when they're not smashing together and sending out waves? Well, so that's what the poor astronomers have been doing, for the past 30, 40 years, finding these places where, for example, there'll be a star which you can observe from the optical or X-ray light that comes off it. And we know it's in a binary system because we can see its spectral lines, and we can see the alternating red and blue shift as the star comes towards us and then goes away from us, comes to and right. So we know it's going around something, and there's nothing there. We don't see anything. And then from the orbit, we use Kepler's laws, and we can infer the mass of the object that we don't see. And there are about a couple dozen cases where the mass of the object that's not seen is too big, if Einstein is correct, too big to be a neutron star. And so those are the cases where we've inferred the existence of a black hole, which I said too much mass in a small volume. But as for directly imaging it or something like that, that's much more difficult. There is actually a project called the Einstein Telescope, which hopes to actually try to image, say, the black hole at the center of our galaxy, to see the shadow by doing ultra-high resolution imaging against the background. And that's, something for the next perhaps 10 or 15 years.
Thank you very much.
There's a time differential shown between the two detector arrays.
Yes.
If theoretically you put in a third detector array and use the time differential, could you get an idea of where?
Yes, great question. So in fact, even from the two detectors, you get a circle on the sky where you can infer where the source was coming from. And by using, there's actually some slight difference in the alignment of the two detectors from the different polarizations. You can even get some more probability, different parts of the circle and so on. Having more detectors gives you more sky localization, and LIGO has a bunch of partners, astronomers, with telescopes of various kinds, radio, optical, X-ray, and so on. And what happens is every time LIGO has a potential detection, they call it a trigger, to distinguish it from a real detection, something which might be a signal, they immediately send out a message to these partners saying, there's something, and they give this sort of band on the sky, and then people can look and see if they can see any kind of counterpart. The localization with the current detectors is not very good at all. I mean, there's lots and lots of stuff in that region. But a little later this year, a detector in Italy, which is an Italian-French collaboration, it's called Virgo, will come online. It will join this collaboration. With three detectors, as you say, you already get much better localization. There's a Japanese detector called Kagra, which is being built. It will come online probably, I don't know, maybe 5 years from now, 6 years from now. And most recently announced is another detector in India, which will probably come online maybe 7, 8 years, optimistically, from now. And so the hope is that in the 2020s there will be this global network, and we'll do real astronomy with these.
This is a wonderful, kind of what another question is, how much approximately do these detector arrays cost? I mean, it's like...
Okay, so the only one I know prices for is LIGO. So for LIGO, the construction cost was $300 million in 1995 or so. The running costs are about $20 million. So you can do the arithmetic, per site, sorry. Yes, that's why he's a director of an institute. He's good with budgets. And then, things like the upgrade, that's, extras and so on. So by the time you add it up, over a 20-25 year period, you're talking about $1 billion.
Hi, this is a random question. I have under the understanding that in the last year, a black hole, they feel there's a digital imprint left on the horizon when something enters it. If you were to throw your wallet, it would duplicate it into a binomial code on the horizon, and the object goes in, and then that gets compacted. Is that? Well, how do you feel about that?
So this is very speculative stuff. I won't even say it's a frontier. You're beyond the frontier, right? So what motivates these kind of speculations is you can blame Stephen Hawking. So Hawking showed that so one thing that's missing from Einstein's theory is quantum mechanics. And we don't have a complete quantum theory of gravity. But there have been some calculations where you partially put quantum mechanics together with general relativity, and Hawking did one of these calculations and showed that black holes are actually not perfectly black. That if you include quantum mechanical effects, there is a small amount of radiation that comes out of the black hole. It's almost like it has a temperature. And for astrophysical black holes, things like we're talking about here, is completely negligible. There's no hope of ever measuring. The temperature is infinitesimal, much smaller than the microwave background radius. It's just purely of theoretical interest. If somehow you had tiny black holes, you might actually be able to see something. But from a conceptual point of view, this raises a problem, because as this black hole is radiating, it loses energy, so it's losing mass, and so it shrinks in size. And eventually, all the mass has been radiated away, and then the question is, what are you left with? Because according to general relativity, inside the black hole, there's a singularity. What does that mean? That just means it's some region where the curvature of space and time has gotten so extreme. It's like in high school when you divided by zero, your teacher would come and rap you on the knuckles, right? Something is broken down. The theory no longer applies. So people have been struggling to try to try to have a complete understanding of what's going on. What happens to all that information that went down the black hole and now is being radiated away? According to quantum mechanics, you can never lose all of that information. But here, you form the black hole, and then this radiation comes out, and it's just like a temperature. There's no memory of how the black hole was made. And so people who believe that somehow that information must be imprinted, there's been all kinds of crazy, people like, right? Some of these were made, some of these proposals come from KITP. Some interesting proposals have been made about how the black hole remembers that information, but we don't know whether any of that's correct.
Appreciate that.
Great presentation. I was interested in the simulating model. How many cells did you have in that?
So the calculation that I showed actually has not too many cells. It's quite modest, something like 75 along each dimension. The reason we could get away with such a small number is we use a fancy numerical method. And our competitors, there are about 10 groups around the world who do this. They all use a different numerical method, and they need to use hundreds of points along each dimension, and so that's why we do that job.
How many calculations does it take to?
So even for us, the easy cases take about a week of supercomputer time. The harder cases take a month or two.
So the lights dim.
Yeah.
Thank you very much for a wonderful presentation. And I just want to make a comment. I expected everyone here to be an Einstein aficionado, and I spoke with at least a dozen people before it started. One knew that right now National Geographic, there's a series put on by Ron Howard all about Einstein, and it's called Genius, and it's every Tuesday at 9 p.m. And I wrote a review on it in the Montecito Journal. If you pick up this week's edition, on page 8, it says it's all about time. Thank you very much.
Thank you.
All right, thank you, everyone. We'll expect to see only about a quarter of you at the Cafe KITP. Thank you very much. Thank you, Saul.
So I'd like to thank Lars for keeping the introduction mercifully short, and I want to say it's a great pleasure to be speaking to you with some of the friends in the audience and my former postdoc advisor. I was a postdoc here in the years 1982 to 1985, and I got a huge amount of value out of KITP. It was just a life-changing experience, and this is my chance to give something back to the community, and so I'm happy to do that. So what I want to talk about is turbulence, and the title of my talk is Beyond Chaos, the Continuing Enigma of Turbulence. I will be mostly talking about the subject itself and the intellectual debate that goes on in the subject, but at the end I'll talk a somewhat personalized view about some of the things that we're debating here at the KITP. So the things I'm going to talk about is my own personal views, and if somebody else equally qualified were to give this talk, they would choose a different set of topics and a different way to present it, but hopefully you'll find this interesting. I will talk about some original work, and that was done with students Hongyan Shi and an undergraduate, Songlin Qi, who is now in the graduate program at Princeton. All right, so we're at the Kavli Institute for Theoretical Physics, and so the question that I really want to ask is, well, you know, why are we, as theoretical physicists, talking about turbulence? What does theoretical physics itself have to say about turbulence? Now, one of the great highlights of my time as a postdoc is when Richard Feynman,